Okay, so I don't know, I'm staring at the camera. Let's continue our discussion on energy and solar system. We are already in the solar system in the sense I already mentioned the orbit. I mentioned sun coming up, sun going down, sun going from one hemisphere to another, seasonal cycle. But we are still doing it from an energy perspective. We'll soon move into more detail. So here we looked at net surplus of energy in the low latitudes and net loss of energy at high latitudes, and we said this means to keep the temperatures from getting colder and colder at high latitudes around the pole, let's say, and getting warmer and warmer in the low latitudes, you will have to constantly move energy surplus or excess energy from here to there. Very nice. That's what gives us winds, and then everything begins to follow. Now, the other thing we need to just mention along the way is that Earth has a tilt. It's rotating around its axis, which is what gives us days and nights, and it has seasons because as it rotates around the sun, we say sun goes north, sun goes south, but actually it's the Earth that is going around the sun, and you have seen this somewhere in your class, I am sure. So the Earth is rotating around the sun on an orbital plane, as it's called, with a tilt at the current time of 23.5 degrees to the normal. If you draw a vertical to the orbital plane, then you get 23.5 degrees tilt. That's the current tilt. Why do I say it's current? Because over time this changes, as we'll see in a minute. So obviously in the boreal summer months, boreal means northern hemisphere things like aurora borealis. We just had lots of news about northern lights because of the big solar storm. We got a lot of northern lights coming to very low latitudes. Typically you have to go to the high latitudes to see them, like Norway and Alaska and so on and so forth. But when the energy is very high and you have lots of northern lights, they are formed because of the energy stripping off electrons from oxygen molecules and creating a dance of light. But coming back to here, in the boreal summer, the axis of the northern hemisphere is pointing towards the sun, so we have our summer season. So the sun goes up to the Tropic of Cancer, reaches the summer solstice, and then begins to head back towards the southern hemisphere, or the Earth begins to move towards this direction. So you get autumnal equinox on September 23rd in the current calendar, which means sun is on the equator, so every latitude will have equal length of day and night. And as the Earth continues to move, by winter solstice, boreal winter, so northern hemisphere winter, December 22nd, the sun reaches the Tropic of Capricorn in the south, maximum latitudinal migration, and then begins to come towards the north again. So you have winter in the northern hemisphere and summer in the southern hemisphere, and then you get to vernal equinox on March 21st and so on. What is the point? The point is, if you look at the sun's rays, then in the northern hemisphere sun, you have 24 hours of light here to the north of the Arctic Circle, which is 90 degrees minus 23.5 degrees, so you get 66.5 degrees. You see the Tropic of Cancer there, Tropic of Capricorn, the equator, and you see the Antarctic Circle here, which gets its summer when that axis is pointing towards or that hemisphere is pointing towards the sun, so you get 24 hours of daylight over there. So tropics are not affected much even though they do see some winter-summer contrasts as we discussed before, right? So this gives us the seasons. On day-to-day time scale, because of the rotation, we have day and night, so diurnal cycle is what we called it. What is the energy got to do with it? It turns out that these so-called orbital parameters, the ellipticity of the orbit, how circular or non-circular it is. If you are not old enough to understand circles and ellipses, don't worry about it. I think you know what a circle is, and if this looks non-circular, it's because it's an ellipse and it has a major axis, minor axis, and so on and so forth. So if grows and shrinks as we see here, so these are animations from NASA Jet Propulsion Lab, Caltech in Pasadena, California. You have to find out where California is if you don't know. It's in the United States of America, which is still in the northern hemisphere but at higher latitudes compared to where I'm sitting in Mumbai, and so on and so forth. So this animation nicely shows that the Earth's orbit around the Sun is growing and shrinking in its ellipticity. The change is only about 0.2%, so, or is it 2%? 2%. So obviously you get farther away from the Sun and closer to the Sun when this happens. This happens on a time scale of about 100,000 years, or as we say 1 lakh years in India. But anyway, just remember that energy coming from the Sun changes because the orbits change as well. And this animation also from JPL, which is actually somewhere, you can't see it here, it is on the other end of the Pacific Ocean here. So this orbit, the obliquity or the tilt of the axis to the orbital plane also changes on 41,000 year cycles. So you can see that it can go to as low as 22.1 and a maximum of 24.5, and currently we're at 23.5. So ellipticity changes, obliquity changes. What else changes? It's called precession. So the Earth itself wobbles like a top. You know, if you play the top, you throw it, when it's rotating fast it'll be upright. As it slows down, it begins to tilt over and do this. There is another precession. This is called axial precession, which happens at 26,000 year cycle. But you also have the orbit itself precessing. So here we said equinox is happening on September 23rd in the fall. In the spring it's happening on March 21st, and winter solstice is on December 22nd, summer solstice is on June 21st, and so on. This orbit itself keeps flipping around because of the gravitational pull from other planets in the solar system, and that means the calendar has to be constantly adjusted, but that happens on a longer time scale, you know, 21,000 year time scale. And all these ideas were put together by a guy called Milutin Milankovitch in the 1800s, 1900s. He was born in Austro-Hungarian Empire, would be current Hungary, a mathematician. Before him there was another guy called James Kroll who had done this also. So the mathematical equations are simple, so we can already say in the next year, next 1,000 years, next 10,000 years how the orbital parameters change, how the energy coming from the Sun changes, and so on and so forth. So just keep that in mind. It's not necessary for weather and climate at the time scales of our lives, but on longer time scales it's very important. And you can see that there is bright snow and ice over here, and Greenland is there, which is covered with glaciers. We'll talk about the difference between glaciers and snow later on, or ice. And this is a good time to think about albedo, the reflectivity. So if there is a bright white surface like this, sun's radiation will be reflected back to space, so less energy is kept by the earth, and you can see that where there is vegetation the surface looks darker, so it will be less albedo, which means more of the sun's energy is kept. Whereas if you look at deserts, Northwest India, Sahara, Middle East, and so on, you see that they are brighter in this figure because they reflect more sunlight as well, and the oceans are typically darker, but that depends on what is the angle of the sun. So if you're flying, if you ever been flying in the aircraft, if you look out the window, the ocean, if you're flying on the ocean, may look very bright if sun is at an angle. It reflects a lot of the sunlight, but if sun is overhead, then ocean can look very dark. So the albedo or reflectivity of the sunlight is very much dependent on what is on the surface and what is the angle of the sun during the day, right? So thermal energy is also going out accordingly, because that energy, the thermal energy produced, is called black body radiation. It depends on temperature to the fourth. If you don't know mathematically what that means, it is basically growing very fast with temperature change. So it just depends on how warm the surface is that is putting out the thermal radiation. Your body is putting out some certain thermal radiation because your temperature of the body is at whatever 36 some degrees centigrade. And if you imagine that pot we had on the stove, when the temperature is low you can't even see that it's warm unless you go close. But imagine a blacksmith who's heating a piece of iron in the fire. As the temperature gets warmer and warmer, the iron can get redder and then white as well, because how much energy it emits depends on its temperature, and that relation of temperature and the energy being put out, thermal energy, is a fourth order, temperature to the fourth, square, cube, and fourth power. Okay, so let's leave this here and come back and look at some more on solar system from these nice book series called the Magic School Bus. So I will take a lot of material from these books because they are written for children, and that will help me be maybe a better communicator with the children as well. So I'm adding some high level material which may be accessible to some of you, and I will also add some simpler things which obviously you would have learned in the class already, but let's use that to also try to reach your younger brother or younger sister, or your students in a lower standard than you. Okay, so whoever can use it will use it. I'll just make these podcasts and put them on YouTube. Okay, see you in the next podcast with the Magic School Bus explaining the solar system.